So I think that's a right amount of time to try some special relativity dynamics problem solving with the ChatGPT. And I do think I still have a few remaining O1 responses, so that'll be perfect. I can use them to ask maybe some of the most challenging questions in your problem set 8. Let's see how ChatGPT does it. So, I hope I have at least like 3 or 4 responses. I haven't gotten the second warning yet, so I should still have at least 5 left. So I'll say hi. I'm back working on special relativity dynamics questions. And I'm doing this prompt so that when I ask ChatGPT the question, it won't answer it fully. The prompt I was using, it's like the two diametric opposite version of what I was using for the timed assessment practice and the actual, practice working through actual problems. In the first one, I was cheating. I just wanted the answer. I didn't care about learning. Here, I care about learning mainly. Let's say for preparation for the one-on-one meeting. So you need to give a ChatGPT a counter instruction that basically tells ChatGPT to not do the thing that most people prefer. You have to tell it to don't give me the answer. I'm trying to work through this myself. I'm trying to learn. So please hold back the information as much as you can while helping me get through the things I'm stuck on. So timeline questions from my calculus-based general physics class. I'm working on these questions in preparation for my one-on-one meeting with my instructor. So please help me learn by not giving me answers right away. I'll try to tell you where I think I'm stuck on. Please just help me with a step I'm stuck on. Respond. And since we don't have that much time, probably enough time for 1 or 2 questions, also enough O1 responses remaining for 1 or 2 questions. Let me skip near the end. I guess I can click through. These first few questions are relatively easy. I think this question is, yeah, I think this is number sense question. And these are, I think, all questions from the textbook. And for this set, I wrote a few questions myself, specifically because I thought the textbook questions were hard enough. They weren't asking you interesting questions. So this is, I think, my 4 momentum primer question, which you should work through. Your textbook, I don't think, covers 4 momentum. And I do strongly recommend that you consider using 4 vector formalism for answering these last 4 questions in the problem set. Is this still? Oh yeah, so this can actually be a pretty difficult question. And I think if I remember right, I borrowed this from another textbook. Not ours, but another textbook. Um, the Yeah, I think this is a kind of question where so I could kind of answer it naively. You could say, part of the mass and absorbs the photon, it increases the mass. Okay, so the photon energy must have been this difference. So you might say, okay, 0.03 times m times c squared. And then it'll say it's wrong. So you ask ChatGPT, I thought E was equal to delta mc squared. What's up? I thought delta E is equal to delta mc squared, according to Einstein, even. Uh, what, what am I doing wrong? It should guide me through setting up conservation of energy and momentum equations. It comes down to, this is rest mass, not its relativistic energy. And it needs to have relativistic energy to basically contain the photon's momentum. Yeah, yeah, right. Rest. Oops. Paste in the question. So oops. Here's the question where I missed. Yeah, before it would just hallucinate something, but yeah, it's not hallucinating. It's yeah, but it's asking the right question because I didn't. I forgot to paste in the screenshot that I was supposed to, and then it should tell me about momentum conservation. Yeah, not at rest. There's a final kinetic energy, and I would really work with the total relativistic energy. Ignores the fact, yeah, moving. It has to, yeah, conserve momentum. Energy must be conserved. Yes, I can. Oh, how much? Okay. E initial plus the photon is equal to E final. Okay. Momentum must be conserved. Yeah, momentum of the photon is P final. Because the final has larger mass and some non-zero momentum. You have to use the full relationship. Yeah, E final is that. Okay. Yeah. Um. So let me try setting up. I think. Yeah, I guess. Let me just try to wrap up, not be difficult. So I'll just try to play act to someone who's a little bit competent. So when it says E initial, then yeah, so you should know that E initial here is is equal to the rest energy of the particle of mass m that is initially at rest. So E initial alone should be mc squared. So I can set up mc squared plus energy of the photon, which is what I'm solving for. So I'll say E gamma is equal to E final. And here I can use the help that hint that the ChatGPT gave me. Gave me this E final expression. So let's just write it out. Um, yeah. So it'll be square root of the rest mass. I'm given that 1.03. 1.03 mc squared and then squared. I'm gonna take square root later. Plus the, let's keep P final, C squared, square rooted. And I guess the place where I can pretend to get stuck is where I'm not seeing the connection between the photon momentum and photon energy. So that's equation 1. I can have equation 2. The photon momentum is equal to P final. So I can even do this. So I'll say I got two equations. I got two equations. See first the image. Um, um, and I plugged in the final to get a single equation. But I don't think it'll work because I don't know P gamma. And let me write out that third, the combined equation that I can paste in for ChatGPT. So plugging in P final is equal to P gamma into over here. You should get mc squared plus E gamma is equal to square root of I guess 1.03 squared m squared c to the fourth power plus P gamma squared c squared. And really what I need to do is I need to use the energy momentum relationship. That's actually in the text. You can use it for photon too. You just have to set mass to be equal to 0, which actually gives you a really clean relationship between momentum and energy. Um, so ChatGPT will probably tell me that, and while it's telling me that, I'll just write it out. Um, E gamma is equal to, yeah, that's my Barney. I think that's gonna be enough for this session, so it'll be fine. If I do run out, I think I can use O3 mini high, but I'm trying to stick with the O1 for consistency's sake this semester. Yeah, for the photon, that relationship. And then once you've done that, then you can basically just solve for E gamma. Don't know why. I thought this question would be harder. Like that you would need to use Lorentz invariant or something, but I don't think it's that hard. So with that relationship, this whole thing would just be E gamma squared. So let's see if it's a doable algebra by hand. Maybe the algebra could get easier if you use Lorentz invariant, maybe. So I'm squaring both sides because doing that will help me get rid of square root on the right hand side. So I'll have m squared c to the fourth plus e gamma squared, and then the cross terms plus um, 2 mc squared e gamma. Yeah, and I think this squared term will cancel. So the square root will go away. I got 1.03 squared m squared c to the fourth plus e gamma squared. These will cancel. So great, I don't have to use quadratic formula. I can just solve for e gamma. And this is simple enough algebra to do in my head. See if yeah, let me not fake mistakes that I wouldn't make. So 1.03 squared minus 1, combining the like terms, m squared c to the fourth divided by, I'm not doing the whole algebra in my head, just a little bit of it. So yeah, I think that'll give me numerical vector 1.03 squared minus 1 divided by 2. And I think I can actually do a kind of binomial approximation to do this. This difference here, it's gonna be very close to 0.06, I think. So I can do, wait, but if I do that, then I get the same thing back. Did I make a mistake? I might have made a mistake. Um, Hope not. Or maybe it's a matter of, let me just do the calculation in a calculator. 1.03 squared minus 1 divided by 2. Yeah, that might actually have been close enough, just outside the 1% limit, to close enough by accident. I think. Um, so yeah, that's good. Yeah, momentum of the resulting particle. So you can use the photon momentum. So it would be the. Do I have photon energy? Yeah, I solved for photon energy. Oh, so actually, it's gonna be silly. It's basically the same thing. You just have to have the correct unit. Because photon momentum is that divided by c, so that's this. I'll say great, I got it. I was like, it turns out 0.03 was pretty close, just outside the 1% tolerance. Thank you, I got it. Turns out 0.003 was pretty close, just a little outside the 1% rating tolerance. Oh, and I guess I can also paste this in if it wants to see my work. All right, I got probably what, 3 responses remaining. That might be enough to get a key help with one question if I'm not unnecessarily difficult and kind of evasive. Yeah. Good. All right, let's find the harder question. That's one of the later ones. Let's see. This feels easy. Missing the yeah. Let me go looking for a harder question. Uh, yeah, this is a harder question for which there's homework help. Um, think between pi on decay and this one, I like this one better. So let's try working through it. And let me imagine I don't know four vector formalism, that how to make things a little bit harder. Let me see if ChatGPT will guide me towards a four vector formalism. So in the left frame, not okay again because yeah, total momentum needs to be conserved. The center, the momentum frame. So what's find the free of each proton? Yeah, yeah. Common enough number that I have it memorized. This is what you get when gamma factor is 2. So it's like square root of 3 over 4 or something. These are the two expressions that I have memorized. Gamma is equal to 1 over square root of 1 minus beta squared, where beta is the speed as a fractional speed of light. And the inverse of this is beta is equal to square root of 1 minus 1 over gamma squared. So when gamma is 2, then this is 1 over 4. So yeah, square root of, so I guess square root of 3 over, not square root of 2. So when gamma is 2, this would be root 3 over 2 when gamma is 2. And I happen to have it memorized to third significant figure because I've seen it so often. Given the speed in A, what is the energy in the x component in moving in the minus? Okay, that seems easy. So gamma factor was 2. Momentum, so it's 2 times that. So it should be 1.732. Thought this question was harder. Oh wait, I think it wants a minus sign. I think the harder part is imagine someone who doesn't know four vector formalism. Then I think a part C might be harder. Yeah, so let me ask ChatGPT that question. Here, it'll definitely, it should guide me towards the four momentum method. But I'll just play confused and say, um, I did A and B of this question. Okay, first screenshot, uh, but C doesn't make sense to me. Um, I'm not dealing with the space-time coordinates here. I just have the formula for relativistic energy, gamma mc squared, and P is equal to gamma mv. I'm not sure what they are asking for because I already used this for B. And it really should tell me about four vectors, four momentum. And I think I have maybe two responses remaining. That might be enough. Yeah, energy momentum, four vector. By the way, this would be a wrong unit. You gotta put them into correct unit first. If you are keeping, c is not equal to 1 unit. Um, yeah, exactly same kind of transformation, but and apply to this new vector. Different, now shift to different frame. Yeah, that's the Lorentz transformation. Correct unit, I guess. Yeah, that's energy unit. Yeah. Um, yeah, I guess that ought to be easy enough to apply. Let's see. So that's 2 minus that, but it's a negative number. Or sorry, let me do this. So it's 1 plus that, so 2.732 times 2. So it should be 5.464. No. Why not? Oh, I had to multiply beta to that. So sorry. Okay, this is outside of what I can now do in my head, because that's the momentum, 1.732. I have to multiply that to beta 0.866, and then add 1.72 times 0.8, and then add that to 1, and then times 2. Oh, I guess this must be just 5. Um, what? Uh, I should just do this correctly. Oh, E is not 1, it's 2. So, all right. I think a third or fourth times charm. That times 0.8, that's the second term here. And I'm adding it not to 1, but 2 mc squared. And then I'm multiplying the whole thing by the gamma factor of 2, but it should be 7. All right. Good. So once you have that, I guess 2 different ways you can find this. You can do this, or you can also, let's just do it that way. Yeah. So let's see, I got my calculator. So I'll just do it, go in a logical order. 2 times the momentum of minus 1.732 minus beta 0.866 times 2 is equal to minus 6.928. That feels right, I think. Good. So I'll say, all right, I got C right with the transformation. And I'll ask, is D just, I'll ask 6. I think it should be 5. 5? No, or, yeah. All right. I think I got C right. Is D just a 6? 7 minus 1 mc squared? And I'm sure that is a mistake without having thought about it too deeply, because I have to subtract out rest energy of 2 protons. Or maybe that is actually right, because I think we're just asking about the one that's moving, not the stationary target. Yeah, all right. I was trying to make a mistake, but didn't. It's fine. Oh, yeah, yeah. So this question is the main thing that makes this question easy is that you are given this parameter or you can figure this out from the central mass frame, and because then you are given the parameter for Lorentz transformation. As long as you are familiar with this four vector formalism, the rest of the question is pretty easy. There are other questions, although not this and not this. Maybe one of the other questions that are in this set. So let me try get a similar question here. There is not like yeah. So this question, I think I would probably do it using Lorentz invariant, but you could do this using the same method as this, I think, because it's basically the same physical process, where the mass of the particle produced is just a little lighter. Yeah, yeah, but the hint I'm giving is the Lorentz invariant. You can do it that way. That's a like one step thing, but you can also break it out this way. All right, I think that's all the time we have. And let's just ask this. I'm seeing, so I'll just say this much. I'm seeing this hint in a different related question. As well, I'll ask, should I have used the Lorentz invariant here? I'm seeing this hint, say, attached in a different but related question. Should I have used the Lorentz invariant here? And it probably will say no. The way this question is broken out, that doesn't save you any work. You can use it. Um, yeah, same result. Yeah, yeah. So this is one where if you don't bother, if you don't want to find out the boost parameter between the lab frame and the central mass frame, that Lorentz invariant is the quick, easy way to do it. If you want to find it out, then you shouldn't use Lorentz invariant. So, so yeah, I think that's it. Again, all the time we have. Thank you so much for joining this session, both of those of you who are joining by recorded video and those who are here in real time. Let me say goodbye to people joining by recorded video, and I will stay online briefly in case our real time people here had any questions. So bye to people joining by recorded video.